Hi, Professor. I'm Liu Lingyue, and the topic of my final year project is distributed Q-learning for fair and efficient multi-network spectrum sharing over frame-slotted Aloha. And here's the outline of my demonstration. Let's talk about the background of this problem first. So there is an explosive explosion of IoT devices which congested heavily on shared and unlicensed frequency bands. And in industrial settings, multiple independent networks may operate in the same physical space. The past researches on multi-network coexistence problem mainly focused on the model-based approaches, and here I listed two major approaches. And in recent years, there have many studies on applying reinforcement learning for network improvements, but existing RL algorithms focus mainly on single network optimization, and in multi-network scenarios, if nodes still use this greedy strategy for transmission, this will bring us lots of collisions and significant unfairness of the spectrum. So here's two classic Q-learning methods on single network optimization, but their performances on our multi-network scenarios is not satisfying. So, but we'll talk about this later when during the benchmark parts. So here's the system model and some key assumptions. We assume that all the networks are under frame-slotted Aloha protocol, and we assume that frame size is fixed to the number of nodes in a network, which means f will be different in different networks. We also assumed saturated traffic where nodes always have packets to send, and our collision model is simple. That is, if more than one node transmits in the same slot, a collision will occur. And another key assumption we made is that we assume all the time slots of different networks share the same length and are strictly aligned using GPS clock signal. And we can see here's the graphic demonstration of our assumption. As we could observe that although different networks have different frame sizes, their slots are aligned in a global view. So under this assumption, we could say that there will only one node which could successfully transmit in a global time slot. So we no longer differentiate between the slot sequences of different networks. Instead, we only maintain this global time slot sequence for transmission indexing and do the collision checking. The major reason we made this assumption is that our reinforcement learning algorithm needs discrete and synchronized time steps. So we have to use this global time slots as a unit time step. But I have to admit that in order to implement our Q-learning methods on our multi-network model, we have to simplify many physical layer dynamics such as distance and power levels, the collision model, as well as this slot alignment assumption. So here's the basic settings of our networks and the objectives. We have three different networks with different nodes and of course different frame sizes. And within each network there is a local receiver to receive the packets transmitted from the nodes and give them the local feedback. And no communication between nodes is allowed, and no global network density awareness is possible. And to reflect the performance of our model, we have these two objectives. The first one is global throughputs. Lambda is defined as successful global time slots over total global time slots. And by the way, later when I mentioned slots, I'm actually referring to the global time slots. Another objective is nodes level fairness. We calculate Gein's fairness index over the throughput of all the nodes of different networks to measure the fairness. And next, moving to our proposed framework. So, how to solve the collision problem with only the local information? The answer lies in our action space design. So, instead of choosing a slot from 1 to F, we expand this action space to let the nodes to have no action, which represents a voluntary backoff. Since we know that the core problem is that the resources are congested, but each node is trying to transmit in each frame. So by offering them this active collision avoidance mechanism, we could improve the throughput of the channel. And here's the results comparison between the modes with and without this no action design. We could observe that the performance of the model with this no action design is way more better than the model without this design, both on the throughput and the fairness. And speaking of epsilon selection, we have to mention the epsilon graded strategy. Epsilon is the exploration probability, and so in our model, it means if the epsilon value is extremely low, the nodes will have low exploration desire, so the slots will always be occupied by some nodes while others are starved. So we can see when epsilon is low, the fairness is in a low level. Well, if the epsilon value is high, we can see that the throughput is extremely low. This is because that most nodes will give up good slots easily, so this will bring us high collision rates. So we do a sweep on different epsilon values to find this optimal epsilon value for balancing throughput and the fairness, which is 0.01 in our model. As for the reward function design, we mapped the environment's feedback into 3 different rewards values. This is a classic reward design, but we have to mention why this -1 penalty is important in our model. As we could see, this is a comparison between with and without the penalty. So we could see if we don't have the penalty, the throughput and the fairness are extremely low. So the reason is that we know that network 1 has the smallest frame size. So in a same time duration, the network 1 will send the most frames. So for each node in network 1, they will have the highest transmission frequency. So they will have the highest throughputs. And since they will quickly find their preferred slot and lock them, so when other nodes from other 2 networks are trying to transmit in that slot, collision will occur. But since we don't punish them using a penalty, so the nodes in network 1 will still not give up the slots even when the collision will occur. What's worse, the nodes of other 2 networks are still trying to transmit in that slot because we don't punish them, so they will keep trying and keep failing frame by frame, which brings the channel lots more collisions. And the reward function is the key factor for updating Q value, but it's not the only factor. As we could see, according to Q value update algorithm, here is this R is rewards values, and this alpha is learning rates. So in our model, the learning rates actually controls the memory length of the nodes. So with different alpha values, we will have different the nodes will have different memory length, and the performance of the model will be different when alpha is low, we could see the fairness is low. But when alpha is in a high level, we could see even the fairness is in a high level, but the throughput is extremely low. So we did the same thing just as we did on epsilon value exploration. So we had a sweep on different learning rates values and find this optimal value for balancing the throughput and fairness, which is 0.3. So we set alpha as 0.3 in our model. And next I will talk about the key insights of our algorithm design. Let's take a look at this transmission probability first. If we assume the number of no actions of the node is k, the transmission probability will be f over f plus k. So we could observe that with more no actions, the transmission probability will be lower. And we've mentioned that the major problem here is, on average, there are 3 nodes competing for one time slot. So an ideal solution is to get the probability at 1 over 3 for all 3 networks, which means we expand the action space 3 times larger. And here's the results comparison between different action sizes. So we could observe that by expanding the action space 3 times larger, we can improve the throughput of the model, and this throughput improvement is about 0.1. But our previous design has two fatal limitations. The first is that we don't know the networks are unknown, so we were actually optimizing the design from a global view. And another limitation is that we could see from this graphic, the inter-network fairness is extremely low due to different transmission frequency of different networks. So we knew that different networks have different frame sizes. So the nodes in network 1 will have the highest transmission frequency. As we give them the equal transmission probability, so network 1 will obviously have the highest throughputs. To solve this problem, we designed this heterogeneous transmission probability for different networks. And our solution is to set no actions of all the 3 networks at beta, where beta is a fixed level. So the transmission probability will be n over n plus beta. This way, different networks will have different probability. And here's an example of our heterogeneous probability design. And the mechanism is that nodes with the highest transmission frequency will have the lowest transmission probability. So in this way, we could balance the fairness and reduce the throughput difference of different networks. And this is the performance of our design with beta is set at 5. And the result is satisfying. As we could see, the J node is now over 0.97. But if we set the number of no actions fixed, we will find it's hard to find an optimal beta for different networks with different n, which means our model is now not robust to different network sizes. So from the graphic, this graphic shows if we change the network size of net3 from 20 to 50, the probability difference will be over 0.4. So the inter-network fairness is still low when n difference is high between networks. And we wish to scale down the network size effects. Our method is to set the no actions at beta times square root n, with beta is equal to 3. So the simplified probability is square root n over square root n plus beta. So in this way, n difference will be scaled to the small level, and there won't be any huge probability difference between networks. Here's the here's an example explanation. In other words, the fairness robustness on network size difference is enhanced. So we test the performance with difference n of network 3 when n3 is equal to 20 and 50. So we could see when n differences goes large, the fairness will decrease at some degree, but overall the performance of our models still works well. As we could see, the J-nodes maintains a high level, which is over 0.91, and the throughput difference when n is large is reduced compared to the previous design. Next, we will benchmark our algorithm against 3 classic Q-learning methods on single network optimization over difference n. As we could see, the throughputs of Aloha Q and LMAC are extremely low because they don't have this no action design, so they can't handle the situation when the resources are congested. Our distributed Q-learning methods and MAB algorithm performs good on this throughputs. But the limitation of the MAB algorithm is that its number of no actions is highly dependent on the network size. So when n difference is large, the fairness of this model is extremely low. So we could conclude that our DQL algorithm is the only method that maintains near optimal throughputs while keeping J nodes strictly above 0.8. Lastly, we will talk about the conclusion of our design and the model performance. So we use this n-scaled no-action design to achieve a high channel utilization without a single network falling to starvation. And in different n sizes, our performance is robust. As we could see, the fairness keeps in a high level. And what's more, we also conducted an comprehensive parameter sweeps for different learning rate and exploration rates to find the optimal alpha value and epsilon value. Lastly, beyond the theoretical success, I would like to mention the industrial applicability of our design. So since we don't need to communicate between networks, so we have a small signaling overhead. This small overhead comes from the GPS signal according to our assumption, and our design is microcontroller friendly since we only use a tiny Q table, a one-dimension Q table for the action selection, and our model has high transferability due to the self-regulating nature of the algorithm. And that's all for my demonstration. Thanks for your time and attention.